Imagine the vast, silent expanse of space suddenly interrupted by a rogue traveler from beyond our solar system. A glowing enigma hurtling toward us at breakneck speeds, defying expectations and sparking whispers of cosmic secrets. Just a few months ago, in July 2025, astronomers thought 3I/ATLAS, our third confirmed interstellar visitor, would make a quiet pass through the inner solar system. But then the unimaginable unfolded. In mid-September 2025, this celestial wanderer erupted in brightness, surging about 40 times brighter than predicted, enveloping itself in a massive green-hued cloud rich in carbon dioxide, spanning nearly half the sun's diameter. Now, as it barrels toward Mars at around 60 kilometers per second, Earth's mightiest telescopes are racing against the clock before it vanishes into the sun's blinding glare. What could cause this alien interloper to shatter every cometary rule we've known? Is it unveiling groundbreaking physics or concealing something profoundly stranger? What hidden drama is playing out near the red planet? And will humanity unravel its mysteries before it's too late? Stick with me through this epic journey, because by the end, you'll see why 3I/ATLAS isn't just a comet. It's a window into the universe's deepest enigmas, and the revelations could change everything we thought we knew about our place in the stars. As of today, September 24th, 2025, 3I/ATLAS is positioned approximately 2 astronomical units from the Sun, twice the Earth-Sun distance, or roughly 300 million kilometers away. It's charging inward at an astonishing 60 kilometers per second, a velocity that boggles the mind and sets it apart from anything native to our solar system. To put that in perspective, that's more than double the orbital speed of Mercury, the swiftest planet in our cosmic neighborhood, which clocks in at just under 48 kilometers per second. If you were aboard 3I/ATLAS right now, you'd zip from Earth to the Moon, a trip that took the Apollo astronauts 3 full days in a mere hour or so. This isn't some engineered spacecraft like NASA's Parker Solar Probe, which required years of intricate gravity assist to reach its record-breaking 200 kilometers per second. No, 3I/ATLAS is achieving this blistering pace purely through the raw pull of solar gravity on its hyperbolic trajectory. As it nears its perihelion, the closest point to the Sun, on October 29, 2025, at about 1.36 astronomical units, its speed will accelerate to a peak of 68.3 kilometers per second, pushing the limits of what we expect from natural objects in the inner solar system. This hyperbolic excess velocity of 58 kilometers per second confirms its interstellar origins. It's faster than both 1I/Oumuamua at 26 kilometers per second and 2I/Borisov at 32 kilometers per second, making 3I/Atlas a true speed demon from the stars. But why does this matter? Because this velocity isn't just a number, it's the key to understanding that 3I/ATLAS isn't orbiting our Sun. It's making a one-way slingshot through our system, bound for the interstellar void once more. Hang on, because as we dive deeper, you'll see how this speed ties into its bizarre behavior. And trust me, the twists ahead will keep you glued to the screen. On the astronomical magnitude scale, 3I/ATLAS has brightened to around magnitude 12.9 as of September 21st, 2025, with recent observations on September 23 pegging it at 13.2, a level that's still invisible to the naked eye, but thrilling for telescope enthusiasts. Let's break this down, because magnitudes aren't just jargon, they're a window into the comet's explosive activity. The scale is logarithmic, where a drop of 5 magnitudes means a 100-fold increase in brightness. So when 3I/ATLAS jumped from magnitude 16 in early observations to its current 12 to 13 range, that's a staggering 40-fold brightness surge, far beyond what models predicted for a typical comet at this distance. For context, the faintest stars you can spot unaided under dark skies are about magnitude 6, so at 12.9, 3I/ATLAS is roughly 250 times dimmer than that, appearing as a faint, ghostly smudge through a mid-sized backyard telescope. Yet this brightness isn't mere optics. It's a direct reflection of the massive amounts of sunlight scattered by its expanding coma, the hazy envelope of gas and dust surrounding the nucleus. Amateur astronomers worldwide are capturing it now in the constellation Libra. But if you're new to stargazing, imagine peering through your scope and seeing this interstellar ghost, knowing it's a relic from another star system. This brightness spike isn't random. It's tied to the comet's volatile ices sublimating under solar heat. And as we explore further, you'll discover how this ties into its green glow and potential for even more dramatic outbursts. Don't stop now. The real intrigue is just beginning. The comet's luminosity tells a story of raw cosmic power, but it's the physical scale of its coma that truly captivates. The nucleus of 3I/ATLAS remains shrouded, with size estimates ranging from a modest 0.32 kilometers to a more substantial 5.6 kilometers, though Hubble data suggests it's likely under 1 kilometer across, a cosmic pebble by solar system standards. Yet, surrounding this hidden core is a coma that's ballooned to nearly 600,000 kilometers wide, half the diameter of the Sun itself. This isn't some optical illusion. It's a tangible cloud of vaporized ices, dust, and gases, reflecting sunlight on an unprecedented scale for an object still 2 astronomical units from the Sun. What makes 3I/ATLAS an outlier? Its composition is dominated by carbon dioxide, with JWST detecting a CO2 to water ratio far higher than in solar system comets, around 7.6, alongside traces of carbon monoxide, carbonyl sulfide, cyanide, and even atomic nickel vapor, but notably no iron. This chemical cocktail, depleted in carbon chains like C2 and C3, hints at an object forged in a distant stellar nursery, battered by cosmic rays over eons of interstellar travel. Picture it, a frozen time capsule, carrying the building blocks of alien worlds, now awakening under our sun's gaze. But here's where it gets riveting. As this coma expands, it's not just growing, it's changing color and structure in ways that challenge our understanding. Keep watching, because the green enigma and anti-tail revelations ahead could rewrite comet science. Trajectory data leaves no doubt. 3I/ATLAS is on a hyperbolic path with an eccentricity of 6.14, the highest ever recorded for an interstellar object, ensuring it's unbound to our Sun and destined for a single, irreversible transit. Its closest brush with Earth comes on December 19, 2025, at a safe 1.8 astronomical units, over 269 million kilometers away. So rest easy, there's zero risk of impact or debris showers. The real drama unfolds near Mars on October 3, 2025, when it zips past at just 0.19 astronomical units, or about 29 million kilometers. A cosmic close call that positions Martian orbiters as our frontline observers. These metrics, distance, velocity, eccentricity, anchor 3I/ATLAS firmly outside the norms of solar system bodies, defying easy analogies. It's like a bullet fired from a distant galaxy, grazing our planetary family before vanishing forever. But the ticking clock adds urgency. As the solar elongation angle shrinks below 30 degrees by late September to early October, ground-based views will fade into the twilight glare, leaving us blind during its most active phase around perihelion. This blackout isn't just inconvenient, it's a race against time to capture data on an interstellar ambassador. If you're hooked on this cosmic thriller, stay tuned. The outburst that started it all is next, and it might just hold the key to its secrets. The frenzy ignited in mid-September 2025 when 3I/ATLAS shattered predictions with a sudden brightness outburst, surging from magnitude 16 to around 12 in days. A six-fold leap that lit up the Comet Observation Database, COBS, with urgent alerts from amateurs in Australia and beyond. Was this a genuine eruption or a photometric glitch? Data poured in, confirming the real deal. An explosive release of volatiles, perhaps triggered by solar heating cracking open fresh ice pockets. As of now, on September 24th, a coronal mass ejection, CME, from the Sun is forecasted to graze the comet, potentially sparking another flare-up. Nature's own fireworks show in space. This timing couldn't be more poetic, coinciding with our current date, adding a layer of real-time excitement. Meanwhile, the Mars flyby on October 3rd looms at 29 million kilometers, close enough for detailed scrutiny, but safely distant from any hazard to the red planet or its robotic sentinels. With its unbound eccentricity exceeding 1.3 ATLAS's, outbound path guarantees no return visits. For Earth, the minimum approach has passed without fanfare, at over 269 million kilometers. No meteors, no collisions, just a precious, fleeting chance to study a stellar nomad. But as the viewing window narrows, the pressure mounts. What if this outburst is a harbinger of fragmentation, or a clue to exotic chemistry? The answers lie ahead, so don't bail now. The global telescope scramble is about to unfold like a high-stakes space opera. As 3I/ATLAS hurtles inward, the geometry turns treacherous for Earthbound observers. The solar elongation, the angle between the comet and sun from our vantage, dips perilously low, hitting below 30 degrees by early October, rendering even powerhouse telescopes like the Very Large Telescope, VLT, helpless against the sky's glare. Perihelion on October 29th arrives with the comet at peak velocity and activity, yet from Earth it's swallowed by solar conjunction, invisible until early November. This unforgiving timeline means the climax, potential flares, color shifts, or even disintegration, plays out in the dark for us. Orbit models, refined from over 600 observations, including pre-covery data back to May 2025, paint an unambiguous picture. No return, no second chances. The urgency stems not from peril but from opportunity, a rare interstellar probe interacting with our sun before eternal departure. To bridge the gap, we turn to Mars' robotic fleet, each craft repurposed for this unexpected guest. Imagine the tension in mission control as engineers reprogram orbits and instruments. This handoff isn't just technical, it's humanity's best shot at decoding an alien worldlet. If that doesn't keep you watching, consider this. The data from these orbiters could reveal physics we've never seen, and we're diving into that next. The data dash kicked off the instant 3I/ATLAS's light curve spiked in September, triggering target of opportunity protocols at observatories worldwide. Hubble Space Telescope, ever the workhorse, snagged emergency slots for ultraviolet and optical imaging, capturing the coma's rapid expansion and estimating the nucleus at under 1 kilometer, crucial for understanding its fragility. Teams battled saturation risks, recalibrating exposures on the fly as brightness soared. Then came the James Webb Space Telescope, JWST, securing a coveted mid-infrared spectroscopy window in August, unveiling that sky-high CO2 to H2O ratio of 7.6, plus detections of CO, OCS, CN, and nickel vapor. Findings that zipped through secure channels to the Minor Planet Center, fueling a frenzy of follow-up requests. Gemini South in Chile pivoted next, leveraging its adaptive optics for detailed coma structure and color monitoring, revealing the depletion in carbon chains that marks 3I/ATLAS as chemically alien to our comets. NASA's SphereX, the infrared all-sky surveyor, tweaked its scans for volatile tracking, providing baselines across wavelengths despite not being built for such nimble pursuits. Each telescope's strengths shone. Hubble's resolution for fine details, JWST's infrared sensitivity for molecular fingerprints, Gemini's ground agility amid fluctuating weather. But constraints loomed. Hubble's limited slots, JWST's packed schedule, Gemini's atmospheric interference. Coordinating this global ballet mirrored planetary defense drills, with directors juggling proposals, data pipelines churning overnight, and Slack buzzing with filter debates. As the glare blackout nears, these final datasets, UV images, CO2 spectra, color snaps, become our earthly legacy. Now the baton passes to Mars, where the real detective work begins. You're halfway through, but the Martian chapter promises revelations that could upend our cosmic views. Stay locked in. When Earth's eyes dim, Mars steps up as the ultimate vantage point, its orbiters transforming into an impromptu comet observatory for 3I/ATLAS's October 3rd flyby at 29 million kilometers. NASA's Mars Reconnaissance Orbiter, MRO, leads with high RISE, its high-res camera boasting 0.3 meters per pixel, potentially resolving the nucleus if glare and motion cooperate. Though tracking at 60 kilometers per second demands simulation marathons and exposure tweaks to avoid damage. ESA's Mars Express, a veteran since 2003, deploys HRSC for wide-field stereo imaging, dissecting the Comet's dust gas layers in color in 3D, timed for optimal orbital plane crossing. The ExoMars Trace Gas Orbiter, TGO, brings CAS-SIS for multi-band Comet snapshots, capturing brightness evolutions, and NOMAD spectrometers to hunt trace gases like CO2 and organics, verifying JWST's high CO2 findings, and sniffing for interstellar oddities. NASA's MAVEN adds ultraviolet spectroscopy for oxygen and carbon emissions, plus plasma sensors to probe solar-wind interactions with the Comet's green aura. Could it be atomic oxygen or something exotic? Orbits optimized for Mars science now divert to this interloper, with teams in the US and Europe holding crisis meetings, patching software, and assessing dust risks. No orbiter alone suffices. Together, they forge a multifaceted view, imaging, spectra, plasma data across time zones. This ingenuity born of surprise underscores space exploration's adaptability. As Earth's view fades, these robotic proxies shoulder the quest, potentially reshaping comet chemistry and interstellar object models. The stakes? Unlocking secrets from another star. If that's not compelling, wait for the color mystery. It'll blow your mind. The Comet's color shift in September 2025 from reddish to vivid green wasn't just pretty. It was a chemical bombshell, signaling profound processes in this interstellar beast. Spanning over 600,000 kilometers, the glow demanded answers. Typically, green comets fluoresce from diatomic carbon, C2, in the Swan bands at 510 nanometers, but spectra from Gemini, VLT, and JWST showed no such lines. Zero C2, despite intensifying brightness. Instead, the culprit emerged, atomic oxygen's forbidden OI line at 557.7 nanometers, born from sunlight and photoelectrons dismantling CO2 and H2O, with a high CO2 ratio, 7.6, amplifying the effect. Lab tests and prior comet studies back this, but 3I/ATLAS amplifies it at 2 astronomical units, where UV efficiently shreds molecules in the dense coma. Alternatives like CO plus fluorescence or plasma oddities were ruled out. No CO spikes, no dust shifts. Debates raged in real-time forums, spectra dissected for hidden C2 traces, but consensus landed on OI as the driver. Dr. Lena Sato from the JWST team called it a moving target with a shifting personality, where fluxing chemistry meets physics on a grand scale. The C2 absence? A badge of interstellar hardship, ices eroded over millennia. Yet the puzzle lingers. Could Mars data reveal stranger lines? This green signature marks 3I/ATLAS as a chemical envoy from afar, and as we probe its anti-tail next, you'll see why some whisper of engineered wonders. Keep going. The climax builds. Defying comet norms, 3I/ATLAS sports a sunward anti-tail, a streak piercing the coma toward the sun, not away, visible in Hubble and ground shots. Classic explanations blame projection when Earth crosses orbital planes, but geometry doesn't match. This persists weeks, hinting at real physics. Dominated by CO2, outgassing is asymmetric. Sunward jets propel large, 10-micron plus dust grains forward, resilient to radiation and heat thanks to dark, non-volatile mixes. Models show exponential brightness fade as grains sublimate, not scatter. Plasma adds twists. Charged grains tangle with solar wind, distorting streams, but core drivers are jet anisotropy and grain endurance. The ion tail behaves normally, anti-sunward, distinct from this feature. Fringe theories, artificial structures, self-organizing plasma, alien tech, surface, but data fits natural bounds, albeit extreme. Dr. Rafael Ortiz from the Mars team stresses, rule out the ordinary before the extraordinary. Perihelion and flyby will test models. If the anti-tail fragments as predicted for CO2 grains, nature wins. Anomalies could spark new physics. This sunward spike, pulsing green, fuels speculation, but science demands rigor. As post-perihelion looms, the true test awaits: fade, flare, or shatter. The implications ripple far. Post-perihelion, from October 30th onward, 3I/ATLAS enters uncharted territory, with models diverging wildly. Some predict a gradual dimming as ices deplete, the coma contracting to a faint wisp outbound. Others foresee a spectacular finale, a brightness surge from deep CO2 reservoirs or nucleus collapse, akin to fragmented comets like Shoemaker-Levy 9. Worst case, total disintegration if porous fractures yield to solar torque, spiking light briefly before debris disperses. Dr. Mara Valente, a leading dynamicist, views this as a crucible for interstellar theories. Simulations forecast diagnostics. Smooth fade signals, standard outgassing. Jumps indicate breaks. Persistent green post-perihelion flags, rich ices, rapid color shifts exhaustion. Beyond one comet, this probes survival of ices in the void, dust solar wind dances, and life cycle predictions for cosmic drifters. Data refines planetary defense, sharpening threat assessments for future visitors. Speculative fringes, probes, plasma life, persist sans evidence, but vigilance reigns. The Mars flyby and perihelion lab score models in real time. Milestones like October data drops, October 29th peak, November revisibility circle calendars, 3I/ATLAS's tail, a live cosmic experiment at stellar speeds, glimpsing alien physics. Yet some visitors evade full unraveling, leaving riddles for eternity. To truly appreciate 3I/ATLAS, let's step back to its roots. Discovered on July 1st, 2025, by the Atlas telescope in Chile at magnitude 18, it was initially dubbed A11PL3Z before confirmation as our third interstellar object. Following the cigar-shaped Oumuamua in 2017 and the active Borisov in 2019. Unlike Oumuamua's passive tumble or Borisov's hydrogen hints, 3I/ATLAS erupts with activity. Its hyperbolic path at 175 degrees inclination, nearly retrograde, slicing through like a straight shot. This rarity, only 3 in recorded history, sparks questions. How many lurk undetected? Surveys like LSST promise dozens yearly, but 3I/ATLAS's extremes test readiness. Its origin? Likely ejected from a distant system eons ago, perhaps by a stellar flyby or planetary perturbation, wandering the galaxy until our sun's gravity snared it temporarily. Comparisons abound. Borisov showed similar CO richness, but 3I/ATLAS's CO2 dominance and carbon depletion suggest unique formation, maybe in a carbon star system or exposed to intense radiation. This context elevates it from anomaly to benchmark, informing exoplanet chemistry and Oort cloud analogs. But the human element? Amateurs worldwide, from Australia to Europe, contribute via COBS, democratizing discovery. As a CME potentially impacts today, September 24th, real-time data could shift narratives. Imagine brightness jumps mid-video. This historical backdrop enriches the saga. Next, we explore implications for life and tech. What if 3I/ATLAS carries biosignatures? Its organics, CNOCS, echo prebiotic molecules, but high CO2 hints at inhospitable origins. Still, as an interstellar sample, it tantalizes astrobiologists. Could panspermia seed life via such wanderers? Nomad on TGO might detect complex organics during flyby, bridging gaps. Technologically, its durability inspires. Surviving cosmic rays informs probe designs for breakthrough starshot. Speculations of artificiality, fueled by Avi Loeb, note irregular brightness and anti-tail as propulsion-like, but consensus holds natural. Loeb urges openness. Extraordinary claims need evidence, but dismissal without data is unscientific. Debates rage on X, with posts dissecting pulses every 232 seconds as engine firings or natural jets. Yet physics fits. Green from OI, anti-tail from grains. If alien, implications are profound. Proof of ET tech scouting systems. But caution, Oumuamua sparked similar hype, resolved naturally. 3I/ATLAS teaches humility. Its lessons could guide future detections. As perihelion nears, global eyes watch. Will it flare brilliantly or fade quietly? The uncertainty thrills. Expanding on observations, VLT's cyanide and nickel detections add intrigue. Nickel vapor, rare in comets, suggests metallic core exposure, while no iron puzzles. Emission rates, 129 kilograms per second carbon dioxide, 6.6 kilograms per second water. Water poor, carbon dioxide rich, inverting norms. This carbon chain depletion aligns with long interstellar exposure, UV eroding volatiles. Gemini's multi-band imaging shows fan-shaped dust ejections, outbursts birthing the anti-tail. Hubble's July 21st image, at 277 million miles, refined size, separating coma glow. Spherix's broad scans track evolution, while amateur Liverpool telescope shots capture daily changes. Coordination via Astronomer's Telegram shares real-time alerts, fostering collaboration. For Mars, HiRISE aims for nucleus resolve, HRSC for 3D coma, CASIS for colors, NOMAD for gases, MAVEN for plasma, a symphony of data. Risks, sun avoidance, calibration, dust. Success could map coma in unprecedented detail, revealing jet mechanics or hidden fractures. Failure, lost chances. This multi-mission effort exemplifies international space synergy, echoing ISS collaborations. Looking ahead, post-November re-emergence offers outbound studies. Fading coma might expose nucleus for radar, like Arecibo once did. If fragments, a debris train could yield spectra on interior. Models predict magnitude 13.5 by late September, dimming to 15 plus post-perihelion, requiring pros. But value endures. Chemical fingerprints inform protoplanetary disks, testing formation theories. Compared to C/2023A3, Suchinshan Atlas, a solar system comet now at magnitude 5 post-2024 perihelion, 3I/Atlas is fainter but rarer. Its story parallels Borisov's 2019 buzz, but with better tech, JWST versus Hubble future. More interstellar finds, perhaps 10 per year with Rubin Observatory. 3I/ATLAS paves the way, highlighting needs for rapid response. Culturally, it inspires YouTube videos, art, even crypto tokens. As a symbol, it reminds, the universe is vast, surprises abound. If it disintegrates, a poignant end. If survives, a resilient nomad. In conclusion, 3I/ATLAS embodies cosmic wonder, a green glowing, anti-tailed marvel, challenging paradigms. From July discovery to October drama, it's a testament to curiosity. We've covered speeds, outbursts, colors, orbits, observations, speculations, each layer building suspense. But mysteries remain. Will perihelion reveal new physics? Mars data hold keys? Thanks for watching to the end. You've journeyed through stars. Subscribe for updates. The universe never stops surprising. What do you think? Is it just a comet or more? Comment below.